So here's a picture of transposition, and let's first follow quantity of blood going through. So let's focus in. Let's start with the cardiac output, and let's look at the aorta. I'm going to put a square around volumes, so let's just use it in terms of units to make it easier. So 1 unit of blood is going out the aorta. I'm starting postductal, and you'll see why in a minute. This blood then goes through the systemic capillary bed, and the same volume returns through the systemic veins and into the right atrium. So there's our 1 unit. Now, at the same time, if the foramen is open, there's a volume of blood that's crossing the foramen. Let's just make up an amount, and it's going to be the amount equal to the amount that's returning through the systemic vein. So let's say an entire cardiac output is able to go through the foramen ovale. So here's 1, an additional 1. And so now the right ventricular volume is 2 units. This then goes into the ascending aorta. So in the ascending aorta, in fact, there are 2 units of blood, or 2 volumes. At the ductus, let's say half of it, or an entire unit, goes through the ductus, and to make it simple, we'll make it all left to right. Now this joins the 1 unit of blood that came from the left ventricle into the pulmonary artery. So you'll notice that there's twice the volume of blood in the ascending aorta as in the main pulmonary artery. But postductal, you have this 1 unit here joining the left to right shunting of 1 unit, so that now the pulmonary blood flow is 2 units and systemic blood flow is 1. So this is our hypothetical situation of a 2-to-1 QPQS ratio. It goes through the capillary bed in the lungs. These 2 units all return through the pulmonary vein. 1 unit continues down through the mitral valve, and the other unit, as we said before, crosses the foramen ovale. And so we land up back here with 1 unit. So now let's talk about percent hemoglobin saturation. What we know is that under ideal circumstances, the blood returning from the lungs, if there's no interference in gas exchange and the lungs are operating perfectly, pulmonary venous saturation is going to be 100%. So left atrial saturation and left ventricular saturation and pulmonary artery saturation are going to be 100%. Let's start with saturation in the systemic vein. Let's say the superior vena cava. Now, ordinarily, if arterial blood is 100% saturated and cardiac output is normal, a systemic saturation would typically be about 70%. In other words, there's an extraction of 30%. The lower this number, the lower the systemic venous saturation number, or more precisely, the greater the difference between the aortic and SVC saturation, the lower is the cardiac output. But let's assume a normal cardiac output. And because this is not going to be a normal number, it can't possibly be in the aorta, because the aorta is going to be what typically the pulmonary artery would have been. Let's say instead of 70%, it's going to be, let's say, 40% saturation in the systemic veins. So what you would have is you would have 1 unit returning to the right atrium at 40% saturation, and another entire unit that crossed the foramen ovale with a 100% saturation. So you now have an average saturation, because there's equal volumes. You will have 70% saturation, or 1 times 100% and 1 times 40%. So 140 divided by 2 is 70. So 70% in the right ventricle, and therefore a 70% saturation in the ascending aorta, and you would see a pulse ox 70%. So 70% in the aorta goes through the systemic capillary bed, extracting oxygen, and returns with 40%. Now on the pulmonary side, again, this is 100% saturated in the left atrium, left ventricle, and main pulmonary artery. But you now have a unit of blood crossing the ductus left to right, but this unit is saturated at 70%, and this unit in the main pulmonary artery is 100%. To make it easy, we made them equal volumes, so you have 70% of 1 times 1 plus 100% times 1. So pulmonary artery saturation is going to be 85%. It's then going to go through the pulmonary capillary bed, which in our ideal case is an ideal hypothetical case is functioning perfectly, so it's going to return at 100%. You'll also notice that the entire amount of oxygen available is coming from this source of 100% oxygen crossing the foramen ovale. So this baby's oxygenation depends entirely upon the volume of blood that can get through the foramen ovale. You'll also notice that the volume crossing the foramen ovale has to be equal to the volume crossing the ductus, left to right. Now let's take a hypothetical situation which is closer to what you encountered in real life a couple weeks ago, where in fact instead of a generous entire unit crossing the foramen ovale, the foramen ovale was very restrictive, or more correctly or accurately, the ductus was very, very restrictive. So an entire liter could not actually fit through there, not liter, unit. Okay, so instead of 1 unit, let's say in fact 0.2 units, or in other words, a fifth of what we assumed here, went through the ductus. So that this now becomes not 1 plus 1, it becomes 1 plus 0.2. So 1.2 units is going to the pulmonary artery through the capillary bed and back through the pulmonary veins. So this is now 1.2 returning to the left atrium of 100% oxygenated blood. That 1 unit of 100% oxygenated blood goes through the mitral valve into the left ventricle, and 0.2 units of 100% blood crosses the foramen ovale. Now you have 1 whole unit of systemic venous saturated blood, which is going to be a very low number, joining the one that's at 100%. And this is no longer going to be 2 units of blood going out the ascending aorta, but rather 1.2. 1 is the cardiac output, and this 0.2 went across the ductus. So now what do we have? We have 0.2 units at 100% that cross the ductus and foramen. In the in the right atrium and right ventricle mixes with that 1 unit of 20%. So you have 0.2 plus 0.2 in terms of total volume divided by the total volume of 1.2. And your saturation is 33%. So your aortic saturation would be 33%, which is actually closer to what we saw. But in fact, that 0.2 units may have been fairly generous. If you review the echo, you'll see that tiny amount of ductal flow. Perhaps it was only a tenth, in which case then you have a tenth, or 0.1 times 100%, and 1 unit of 20%, so 0.3 divided by 1.1, or 27% systemic saturation. Now, even that is generous, because with a systemic saturation of 27%, you're probably not as high as a systemic venous saturation of 20%. So let's make it 10%, so that the extraction is from 27% to 10%, in which case you get 0.1 units that's crossing the ductus at 100%, and 1 unit at 10% systemic venous saturation. This mixes up to be 0.2 over 1.1, or about 18%, which would be the pulse ox. Now the question then came up, how did this baby have a pulse ox prior to going home of reportedly 98%, and was that possible? So I'm going to leave that as homework for you, but remember, in order for that saturation up here to be so high, this volume crossing the ductus would have to be very, very high. So now play around with the numbers and make this a 3-to-1 shunt, or a 4-to-1 shunt, or a 5-to-1 shunt, and see how the numbers work out and how great the shunt would have to be in order to get this number up to 98. Frankly, it's not really possible, but do the homework, and we'll talk about that on another occasion.